In the previous video we used this configuration to look at configuration of static function elements. So what I'm going to do is use the same configuration but replace the static one with a dynamic function. So let's just get rid of this, and you can see all the links have disappeared as well, and let's put in a dynamic function in here. Let's just use L3, so we'll move that one up just now, and we'll configure this thing, and we'll take a measurement, just take a single input in there just now, and we'll send an output out there. We'll call this an X value because who knows what we're going to be using. Input is 0 to 5 and it's a level measurement, and output will let it go 0 to 100, and we'll just use percentage for the moment. Okay, so what we can do then is in the dynamic function we can choose 3 different types of function. We can have an integral unit, a time delay unit, or a lead lag unit. So let's look at the integral unit first. Our integral dynamic function is shown here. What we've actually got is the thing represented as a Laplace transform. So what this is doing is it's multiplying input 1 by constant A, adding input 2 multiplied by constant B, input 3 multiplied by constant C, and then it's taking the integral of that summation. So in this particular instance we're only using input 1, so let's put the constant of 1 on there. Because this is a dynamic function, it will have an initial value, so that has to be set at what the appropriate initial value is for what you're doing. In this case all I'm doing is actually integrating the input signal, so really this initial value would have a value of 0. I guess you can make it anything you want, but I'm just going to leave it as 0 at the moment. No, I don't want to change it. Okay, so there was a wee warning there that my initial value was 0, and did I want to change it? Okay, so let's connect the thing up. Let's connect this thing up. Now what I would expect this thing to do is that we have a nominal steady state value of 2 on this thing. If we're integrating this thing at a 1 second sample rate, we would expect to see this increase pretty much in a straight line because the input value isn't changing. So let's run that just now. Let's put that back into edit mode and we'll run it. Okay, so he's starting at 0, 2, 4, 6, 8, 10, 12. It's just integrating it with a 1 second sample time, so the delta t is 1 second. So obviously you can use this integrator for all sorts of things. You could calculate ISE, I guess. You could use it as part of some weird wonderful control scheme. I have no idea why you would use the integrator in a control scheme like that, but I guess you could if you wanted to. But it's there if you want to use it. Other things that we can do in this is put a time delay in. Let's put a time delay in this one. So the time delay signal, what it does is it adds together A times I1 plus B times input 2 plus input 3 without a constant on it. But then it actually lags the output by C seconds. Okay, so at the moment there's no lag on there at all, so let's make this 10 seconds of lag. The initial value in the output, let's set this to have an initial value of 1. Let's say, just to show you how the initial value thing actually works. And that's really all we have to change on it. So what I'd be expecting to see with this one is a signal, an output that is at 1 when the simulation starts, and then 10 seconds into the simulation run that will shoot up to what the current value of the input is, which is 2. And this thing will track that value dynamically as well. So let's just run that. You can see that it's showing a dead time on there. So let's run that thing. So we're starting at a simulation time of 44. So that's ticking away there. And at 54 you can see that this output has jumped from 1 to 2. So really it's just implementing the dead time. Why would you want to implement the dead time in a control configuration? Well, you might need it if you're putting in a dynamic feed forward scheme, if the disturbance and manipulation signals have different delay times that they affect the output response. You might also want to use it if you're putting in dead time compensation into a control scheme as well. The last one, which I'm not going to bother showing you how it works, but I'll just talk about it briefly. The last one is the lead lag element, and this implements a lead lag transfer function. Now the transfer function is completely implemented through constants. Okay, so you've got a gain, which is A, plus the lead part of it, which is Bs plus 1, divided by the lag part, which is Cs plus 1, times the summation of the 3 input signals. Now lead lag element would be used in something like a dynamic feed forward controller, where you're trying to build in some sort of process dynamic model into your control scheme. So that would be an obvious place where lead lag units are used. Okay, so that's the 3 dynamic functions that are present in PySim. The other thing, I'm sure in an earlier video I mentioned that the derivative was a dynamic function. It hasn't actually been implemented that way. It's been implemented as a static function, but it's in there in the static function blocks if you need to use the derivative function. Okay, thanks for listening.